Okay, we're going to talk about the combined gas law. And the combined gas law is going to be looking at three variables at once. Okay, so we're going to be looking at pressure, volume, and temperature all at the same time. And when we change those variables at the same time, what happens to a gas? Now, I know this sounds very complicated, and it sounds as if it was something that you almost couldn't solve because you'd be saying, well, if two variables are changing at once, how are we going to keep track of them? Well, the way that we're going to keep track of them is we're going to be using the combined gas law equation, which is P1 times V1 over T1 is equal to P2 times V2 over T2. And if you look at this equation, you can see that it has the previous three gas laws all, dun dun dun, combined. That's right. If you were only to look at the top, you would see Boyle's law. If you were to look at P1 over T1, you would be looking at the Gay-Lussac law. And if you were looking at V1 over T1 only, you'd be looking at Charles' law. You can use this gas law, the combined gas law, if you were ever required to memorize these, you could use this combined gas law to actually derive the other three gas laws that we've studied. Because if pressure was held constant, then you could remove the p value from this equation because constant means it doesn't change, so it's the same on both sides. And that would give you Charles' law. Okay, so if temperature was held constant, you could remove the T from this equation and you would have Boyle's law. So you could use this if you were required to memorize gas law equations. We, however, are not required to memorize them. So what I'm going to do is I'm going to show you what these things represent. Okay, so here we go. When we look at the combined gas law, of course you're going to see P1, okay, and that is the initial pressure. Sometimes you call that the starting pressure. Now, what kind of units can be used for pressure? Atmospheres, kilopascal, torr, millimeters of mercury. Anytime you see a number with one of those units, you're looking at a pressure unit, okay, or pressure value. We talked about that before, but this is a little bit of a review. P2, of course, is the final, or sometimes called the ending pressure. And it would be in the same units that I just talked about. Okay? T1 is the starting, let's use the same word here. Instead of saying starting, let's use, it is the initial temperature. Okay, and so what would be temperature units? Degrees Celsius, Kelvin, even Fahrenheit, okay? Degrees Fahrenheit. Those are all temperature units, but you have to remember the temperature in these gas laws must be converted to Kelvin. And I'm putting that in capitals. It's like I'm yelling it out loud because that's how important it really is. You need to remember that these things have to be converted to Kelvin or you cannot use them, okay? That's the most common mistake for gas laws that students make, is they don't convert it to Kelvin. So make sure you do that. All right, so then, of course, T2 is going to be the final temperature. And you have to convert it to Kelvin, okay? All right, so what are we missing? Well, we're missing V1. V1 is initial volume. And so volume, the units for volume are commonly liters or milliliters. It could be deciliters, okay? So these are all units for volume. So that's initial volume, and then V2 is final volume, okay? Same units. All right, so let me go ahead and highlight these units for you too, because I've been finding that there are students who still don't know the units, okay, and what they represent. So make sure that that's not you. You want to know those units so that when you see a value, you know what it is trying to tell you. It's trying to tell you maybe pressure, volume, temperature, okay? I also want to add the conversion for Kelvin. So Kelvin is equal to Celsius plus 273, okay? So that's what you're going to use if you have to convert. All right, very good. So with that, knowing that, having this formula, we can solve some seemingly complex problems, okay? So I say seemingly complex because when you read them, they are probably going to maybe get you a little nervous. But as long as you follow the steps that I've given you, you're going to be able to solve this no problem. So here we go, okay? All right, so let's look at what we have here. So we have a gas at 110 kilopascal. So I'm going to go ahead and write that down. Kilopascal is pressure. So P1 is 110 kilopascal, okay? And then I'm seeing that we have a temperature, okay, at 30 degrees Celsius. So we're immediately going to change that to Kelvin. Get out your calculators. Get your fingers tapping. That's 303 Kelvin, okay? And then this gas is in a flexible container with a volume. There is volume, V1. Volume is 2.00 liters, okay? All right, so all I did right there is read through the problem and write down what I know by looking at the units, okay? You can see that this is a pressure unit, this is a temperature unit, that's a volume unit. Okay, so now something happened. The temperature is raised, so that is T2, right? They changed the temperature to 80 degrees Celsius, so plus 273, okay? 80 plus 273, tap your fingers, 353 Kelvin. Okay, pretty straightforward, right? But what did they also do? They increased the pressure. Oh my goodness. They're making this complicated. So the pressure now is 440 kilopascals. Okay. And what is the new volume? Okay, so V2 is equal to question mark. All right. Well, let's look at what happened here. They took the pressure and they increased the pressure. So you know from Boyle's law that if you increase the pressure, you decrease the volume. So just that part should tell you that the volume is going to go down. But what did they do to the temperature? Well, they took the temperature and they increased the temperature. So that's temperature versus volume. If you increase the temperature, you're going to increase the volume. That's Charles' law. Uh-oh. So you got one thing trying to make the volume smaller, and you've got one other thing trying to make the volume larger. So it's like a war. Who's going to win the war? Boyle's law or Charles' law? Well, let's find out. Let's put in the information, and let's solve for what we know. Okay, so this is step one. Okay, let's go to step two. Step two is to write down what we know. P1 V1 over T1 is equal to P2 V2 over T2. Okay, so what I'm going to do right now is I'm going to just slow it down in case you are scratching to catch up. I'm going to let you catch up, okay? All right, so this problem, okay, this exact problem you can find in your textbook, all right? And this exact problem is in the gas law chapter under the category of combined gas law. So you could go into the textbook and you could find this exact problem. All right, guys, it's already written for you. All right, now we have to play the game of plugging in numbers. So where there's P1, we're going to plug in the number 110 kilopascal. So you need to go slow here, okay? Because you don't want to make a foolish mistake, all right? Don't make a foolish mistake. So here we go. I'm going to go slow. So I've got let's change this. I've got 110 kilopascal, all right, times V1, which is 2.00 liters, over 303 Kelvin. Okay, now take a second and make sure that that works for you. P1 is 110, V1 is 2, and T1 is, 303 Kelvin. Check your work, okay? All right, so what's P2? The second pressure is 440 kilopascal, okay? And V2 is, well, guess what, guys? V2 is X. We don't know what V2 is. Make sure you write it down. There was a student who wasn't writing down the unknown, and that was really messing them up for doing the calculation. So be sure you write it down. And then T2 is, I see that T2 is 353 Kelvin. Okay? So just go back and check and make sure that you feel comfortable with what just happened right there, that these numbers plug in the way that you would expect. Now, let's do this. Since we see an equal sign between fractions, we can cross multiply this part. So let's do that. Ready? Oh, I don't need you. Here we go. 110 kilopascals times 2.00 liters times 353 Kelvin equals. All right, you guys see what I did? Nothing complicated there. I just multiplied them like I said I would, right? Okay. And then you can also cross multiply this side. Okay. So 303 Kelvin times 440 kilopascal. Now go nice and slow, times X. Okay. All right, so there we go. We've got these giant multiplication things. So let's do the multiplication right now, okay? Get your calculator and multiply 110 times 2.00 times 353, and then don't forget the units, okay? So get your fingers tapping, all right? While you're doing that, I'm going to go ahead and do mine too. And here's our equal sign. So what I am seeing that we get is 77,660. Oh my gosh, look at these units. Kelvin times kilopascal times liters. Okay? Why do I have to write those down? Because nothing cancels, right? So the Kelvin remains, kilopascal remains, liters remain. All right, what about the other side? Let's multiply 303 times 440 times X, okay? Ooh, an even bigger number, 133,320 Kelvin times kilopascal times X, okay? All right. You know what? That was just multiplication, guys. I don't think that is without outside of your abilities. But now we got to do a little bit of algebra, okay? Because we want to isolate this variable right here. We want to isolate x. And the problem with that is we've got something attached to it by multiplication. We've got 133,320 Kelvin kilopascal stuck to this x. So the way you undo multiplication is with division. Watch me very carefully. Now, I had a student who also put x in the denominator. If you put x in the denominator, then you cancel x and you've got nothing to solve for. So do you notice that I did not do that? All right, now if you do it on the right, you got to do it on the left. So here we go. That's why there's an equal sign, right? Just take your time, guys. Do everything nice and neat. Don't put an x down there, guys. Why would you do that? Okay, that would be I'm going to say it. That would be a dumb move. All right, so the number cancels out here, the units. The only thing we have left on the right is X. And now look what cancels here. Kelvin, kilopascal, we have liters. Now do the math, and you should get this number, 0.58250. And we only need 3 significant figures. So 1, 2, 3, look at that number, it's a 5. So that 2 becomes a 3. And then we have liters equal to X. So what happened? Okay, if you do this, the volume is going to get smaller. All right, if you put high pressure on it and increase the temperature, well, it seems like pressure has the bigger influence and the volume got smaller. Okay, and there's your final answer. Now, if you were to show this work to your parent or guardian, they would probably say, "My child is a genius. Look at all this crazy stuff that's here." But you should know secretly inside that if you follow the procedures I've given you, this problem is no more than plugging in numbers, doing some like 8th grade algebra, and just making sure that you round correctly. And that's how we solve a combined gas law problem.